Hello, and welcome back to a video series on MAC 1140 Precalculus Algebra. My name is Sean Perry. These are guided notes number 27 in the series, Final Exam Review, Part 1. Our review begins with some problems on factoring. For number 1, by far the easiest way to do this is to recognize that we have a difference of two squares here. 49x squared is 7x squared, and 36 is 6 squared. The difference of two squares formula factors as such. We really just need to plug in numbers here. Problem number 2 shows us that the difference of square formula can be applied several times. Here we see x to the 4th power and y to the 4th power, with a difference between them. This sets up this kind of problem. We can see 256 times x to the 4th is 16x squared squared. And likewise, y to the 4th is y squared squared. So plugging things in, we get these two terms. And notice that one of them is again a difference of two squares. This can now be factored again, while the sum of two squares, though it would factor over the complex numbers, doesn't factor over the real integers. So this is our final answer here with these three terms. Remember that in general, factoring is foiling in reverse, or expanding a polynomial in reverse. We want to write these as a product. And if I leave some slots open here for my coefficients, we can begin by fixing the signs. We'll need at least a positive because the inner and outer part of the foiling are going to sum to give me a positive. So we know at least one of these second terms is positive. And likewise, we need these terms to multiply and give me a last term which is negative. So the second term here will have to be a negative. This is a good step to do first because it lets us know that we're looking for a difference of factors of 6 that give me this middle term of 5 and not a sum. So this isn't going to be 3 and 2. It's going to be 6 and 1. And if you follow this protocol of putting this sign into the first position, you always know where your larger of the two factors is going to have to go. Don't be confused by the fact that there was a y in this problem. If we see this pattern of squares and then a first power and then nothing, and that's matched on the other side kind of homogeneously by a square and then a y here with no square and then nothing, so all of these are degree 2 terms, what we're going to wind up with is a symmetric pattern in x and y. You can factor this the same as you could any monic quadratic polynomial in x just by putting a y in the second position. Foil it out and see if you can see this pattern in action. To factor number 4, the first thing we want to do is get a common factor out of both terms. They both have an x, and dividing that out, we get x squared minus 64, which is again a difference of squares. Question number 5 asks us to divide two complex numbers, and the trick for doing this is to multiply on the top and bottom by the conjugate of the denominator. The conjugate just means changing the sign of the imaginary part. And when you multiply that out, what you'll find in the denominator is a real number. This is great because after foiling out the numerator, we'll wind up with a complex number that we could divide each term by this denominator's real number. We can't split up sums in a denominator, but we can split up sums in a numerator by dividing a single denominator into each term. And that gives us these two numbers. We like to pull out the I, and we like to separate these numbers by splitting them into two parts because all complex numbers in their standard form are written as a real number, plus b, a real number, times I. Question number 6 asks us for a degree 3 polynomial with real coefficients having zeros at 2 and 3i. A fact that we have to know is that real coefficient polynomials, if they have a complex root, will also have its conjugate as a root. So let's write out the factors. If it's got a 0 at 2, it has a factor of x minus 2. If it has a 0 at 3i, it has a factor of x minus 3i. And its conjugate, minus 3i, will give us this term here of x plus 3i. To get our degree 3 real coefficient polynomial, we really just need to expand these terms. Expanding these two complex terms gives us a sum of squares. That's interesting. And then expanding it the rest of the way, we wind up with this polynomial here. Question number 7 asks us to solve a polynomial inequality. And they've already done us the solid of factoring that polynomial. Notice that we have a first degree term, and a second degree term, right, with multiplicities 1, 1, and 2. And that tells us the behavior at each of these zeros. At the 0 at 10, it's going to cross. The 0 at -9, it's going to cross. And the 0 at positive 4 is going to just bounce off of the axis. It's going to touch it and then bounce off of it. And that corresponds to having odd, and even multiplicity respectively. The way I like to proceed from there is by looking at the leading term. You can take a look at the x times this x squared, and we'll find that this thing is going to look like positive x to the 4th plus lower order terms. What this tells us is that it's going to go up and up on the right and left respectively, and that's great because now we have all the pieces we need to solve the inequality. Notice it's a strict inequality, so we're not going to include the zeros. And here I've drawn a quick sketch of the graph with no real scaling on the vertical component. None is necessary. What we know is that it's going to be positive over here, and then at -9 it's going to cross, and then at 4 it's going to bounce off, and then at 10 it's going to cross again. So this tells us where it's positive and where it's negative and where it's 0. That's everything you need. That's going to be between -9 and 4, between 4 and 10, but not between -9 and 10, because we have to omit this 4 here. So we could write that this way, omitting the 4 with a parentheses union parentheses kind of symbol structure. And if we wanted to graph such a thing, then we could do it with these two conjoined intervals. Make sure you're leaving open circles to show that we're not including the zeros as solutions to this strict inequality. At the same time, we're using parentheses here in the interval notation. Question number 8 asks us to solve a rational inequality given this graph. I'm presuming it's rational. It looks like a rational function with these asymptotes here. But even if this was just any old function, we could solve this inequality from a graph. We're just being asked about where is it greater than or equal to 0. In other words, where is it positive or 0, that is non-negative. Well, here, you can see it in the upper half, and so can you here. And we presume that this asymptote just continues like this one does on this side, off hugging towards the x-axis as you go towards positive infinity. So how does that let us solve the problem? Well, we need to write down where is it actually positive or 0 in interval notation. Notice we're always going to leave out the asymptotes because the function is not defined at that point. We are, however, going to include the 3 because it is going to be defined there, and this is a inclusive inequality. We're going to omit the 5 because that's an asymptote. It's not defined there. And then it proceeds on to infinity while remaining positive, or so it would seem to be indicated from the graph. If you wanted to plot such a set on the number line, I would do it in the following way. This interval goes from 2 open to 3 closed. Then we skip a little space here and start again at 5 open to infinity, which we show this way. Question number 9 asks us to factor this cubic polynomial, and they've already done us the solid of splitting this into 2 terms that are both squares, which lets us know how to factor it by grouping. Factoring by grouping is something I would try if they gave me any old cubic function that had 4 terms in it. If we cut this expression in half, we're going to see that we could factor a greatest common factor of 3x squared from the first half and a 5x out of the second half, which leaves us a repeated x minus 1. This repetition is what we need in order to complete factoring by grouping, because we can pull out this, again, using the distributive property. This gives us 3x squared plus 5x as a single term, and x minus 1 as another term. Now, 3x squared plus 5x has a common factor of x, so we could pull that out too, and that completes our factoring. Question number 10 asks us about the process of completing the square. I've included this little addendum here to the text from the homework because I don't like the idea that you're just adding something. We're really never doing just one thing in math. We're either doing it on both sides of the equal sign for balance, or we're adding 0 in the form of adding and subtracting something simultaneously. And we should keep that in mind even as we proceed to do some kind of algorithm so that we can factor. The algorithm in particular is that when we have a linear term like this, negative 14 over 15, for example, we're going to want to take half of that and then square it. This will give us a perfect square trinomial and another term when I add and subtract it respectively. Now, 14 over 15 divided by 2 is 7 over 15. That just reduces. And then we square that to get 49 over 225. So this would allow me to factor this trinomial as z minus 7/15, or the half term here, squared minus 49 over 225. Keep track of this 49 over 225. I'd like you to keep in mind that that thing exists. Question number 11 gives us another seemingly polynomial inequality, but regardless of what the function is, we can proceed to solve this with the graph. We can see that it's positive in this region and negative in these regions here, and it's 0 at the places I've circled. I've circled them open because this is going to be a strict inequality. We're going to leave those points out. Where is it negative then? It's going to be negative in this region here between -2 and +1, and it's going to be negative again thereafter. It's not going to be negative at 1. It looks like it's going to be 0 there. So we need to omit that point, like these conjoined intervals. And our graph on the number line looks like array with this point at 1 removed. Question number 12 has a rational inequality for us to solve. I would begin by factoring everything I could in the polynomials on the top and bottom. And then I would have x minus 2 over x minus 5 times x plus 5. All of these are multiplicity 1 factors. This means that we're going to change our sign as we go through each one of these either zeros in the numerator or asymptotes in the denominator. Now, to get this started, we're going to want to plug in a test point, and 0 is a particularly easy one to plug in. Replace the x's with zeros, and we have -2 over -5 times +5, which all we really need to know about that is that it's positive overall. Negative over negative times positive is going to be overall negative. And then we know that it's going to change sign around each of these critical points. We're not going to include any of them, both because some of them are asymptotes and because this is a strict inequality. So we'd leave all of them off anyway, even the zeros. And that gives us the following regions which are negative and the following regions which are positive. They asked us about the positive solutions, so we're going to go from -5 to 2, and then also from 5 to infinity. Question number 13 asks us to evaluate this composition of functions. The outer function is just some polynomial, and the inner function is just some linear function. All you have to do to evaluate this function notation is to plug in whatever you see inside the parentheses to the rules that dictate what f of x really is. So plugging in x minus 1, everywhere I see an x here, I'm going to have to square these terms, distribute my coefficients, and then gather like terms. But after that, we get a new polynomial, which is our answer. Question 14 is a question about inverse functions. The definition of an inverse function is one which cancels another function down to the identity function y equals x. This just takes in an x and gives us back an x. So it's been effectively canceled when I compose the two functions together. We just have to make sure that that actually happens. So plugging in x plus 8 over 3, which is the rules for g of x, into f of x, I then compose that with the rules for f of x, which is times it by 3 and minus 8 from it. When I do that, my 3's cancel and then my 8's, and I wind up with x itself. Likewise, if I take 3x minus 8 and I plug that into the rules for g of x, add 8 and then divide by 3, first the 8's cancel, then the 3's, and this just gives me x back. When both left and right composition give us our identity function, y equals x, we found that these two are inverses of each other. Question number 15 gives us an exponential equation to solve, and they've already done us the solid of putting the bases equal to one another. That's great, because exponentiation is injective, or 1 to 1, which means if the two bases are equal, then their exponents must also be equal. This gives us the equation x squared is equal to -2x plus 8, which we could factor the usual way. Once we bring this term over to the left-hand side and factor and set these two factors equal to 0, we find that x could be either -4 or 2 to make this work. And we could even check that by plugging these in, 16 and 16 here, or 4 and 4 here when you plug in -4 and 2 respectively. But for these exponential equations, as long as we can get started, then we really can just kind of trust our answers. It's not so with logarithmic equations, where we have domain restrictions to consider, but you're pretty safe with the exponentials. Here's another exponential equation. If we sort of squint our eyes and cock our head to the side, we can see that they're both powers of 2. 4 is 2 squared, and 1 over 8 is 2 to the -3rd. Using our power to a power is the product of powers property, we can see that this is going to give us the equation 2x is equal to -3 times 5x plus 2. Distributing and Combining our like terms, bring them over, we solve for x to give us negative 6 over 17. 17 and 18 ask us to rewrite equations given in one form, say exponential, into another form, say logarithmic. No matter what, you can take exponential equations and write them as logarithmic ones and vice versa. So this logarithmic equation here has a base of y, its output is n, and its input or argument is w. If you reverse the roles of output and input, you need to use the inverse function. And so this is going to be the inverse of log base y, which is y to the power of. Y to the power of the output is equal now to the input w, gives us our exponential form. In the exact same fashion, if we have a 9 in the base of the exponent, we would want a 9 in the base of the logarithm. The output here would become the argument of the log, and the n here, the input to the exponential, will become the output of the log. Question 19 asks us for an evaluation of this logarithm, and the easiest way to do that is to write this in exponential form. Your properties of logs tell us that logs cancel with exponentiation as long as our bases are the same here, and so knowing that 1 over the square root of 2 is the negative 1/2 power of 2, we can get our evaluation of the logarithm easily. Let's also not forget how to evaluate logs on a calculator. If we have a TI-84, we can likely go to Math and then down to Log Base, which gives us a slot to write in our base of 2 and our argument, which is 1 over the square root of 2. This is, of course, minus 1/2 as we got. And if you didn't have a TI-84, you just had access to a scientific calculator, that really wouldn't be a problem. We would just need to apply the change of base formula. We could take either the common log or the natural log of 1 over the square root of 2 and divide that by the common log, or if you like, the natural log, of the base originally was 2. Gives us the same result. Question number 20 asks us to determine the domain of this logarithmic function. Logarithmic functions, for this course, have to be positive in their argument. That is to say, whatever you see here inside of a logarithm, that's actually asking you to evaluate an inequality. Where is that greater than 0? Log of 0 is always undefined, but logs of negatives are actually multi-valued complex maps, which, if you continue on with your mathematical studies, you'll see how to evaluate one day. But for now, we're going to insist that these arguments stay positive. That involves solving this inequality, which is a quadratic polynomial. We're going to need to factor this guy, and so that's going to require us to maybe use the AC method, maybe use whatever method you like. Hey, even use the quadratic equation if you want to, but we're going to need to get these zeros somehow. I like to put an 8x or a term times x in each one of these slots and a 1 over a out front so that it's actually true what I just wrote down. Then we can look at the product of 8 times 15, which is 120, and we're looking for factors that have a, after fixing my signs, the same sign sum of 22. This was a minus, this was a minus, and so we're looking for factors that add to be 22. That keeps us from having to keep too much track of what sign is what. So what are those? That's 12 times 10. That gives us 120, 8 times 15, but it also has a sum of 22. And now all that's left to do to complete the method is to reduce these two terms. I can pull a 4 out of this one, I can pull a 2 out of this one, and that gives me an 8, which cancels the 1/8. Reducing, we get 2x minus 3 and 4x minus 5, which solve to give us 3/2 and 5/4 respectively. Now we want to know how the inequality actually gets solved, since we've just found the zeros. It's a strict inequality, so we're going to use parentheses. And the notion is that since this is a upward-facing parabola, we know where it's going to be positive. It's in the wings. So this is going to be from negative infinity up to 3/2, and also then from 5/4 up to positive infinity. We could write this using interval notation, we could write this using set notation, we could graph it, but we're going to have to keep in mind if we were solving any expression that involved this f of x, we'd have to make sure that the answers we got obeyed this additional domain restriction. That's the point of doing these domain type problems for logarithms. When we solve logarithmic equations, we might get solutions that don't match the domain, and we need to throw those away. Number 21 gives us an evaluation problem that requires us to know the properties of logarithms. They say if log of a is 3 and log of b is 2, what is log of a to the third times b to the fifth? Well, a to the third inside the logarithm becomes 3 times a outside. Likewise, b to the fifth becomes 5 times log b, and since there's a product between them, that can be written as a sum between these two separate log terms. Now that we've written things in terms of log of a and log of b, we can substitute those known values in to get 19 in total. Question 22 asks us to condense these into a single logarithm, which is an important first step for solving logarithmic equations. Now, the products come inside as powers. The subtraction here is going to come inside as division. Don't forget that a 1/8 power is an 1/8 root, and that gives us our overall expression. Once you understand the patterns thoroughly, you can sort of proceed to one-step this kind of problem. All right, that's going to do it for this video. Thank you very much for your patience, and have a great day. Good luck with your studies. I'll see you in the next one.